Hello. So in this example, we are wanting to calculate a limit, and we have this sort of huge right, polynomial over polynomial. And it sort of gives it away, right, because it says to use L'Hopital's rule, but typically when we're going to compute a limit, it helps to just plug it in and see what happens, because sort of even though it almost certainly won't sort of just work, sort of how it doesn't work sort of tells us what to do, right? So good first sort of step in the process, plug in and see what happens. So we want the limit as x goes to 2, so I'm going to try plugging that in. So in particular, I'm going to look at, so like maybe in fact I'll even, no, I'll do it on this side. But make note, I'm not going to claim the limit equals this, right? This is sort of scratch work on the side. You wouldn't even necessarily need to like show this work depending on what you're doing. So anyway, so I plug in 2, so I get 2 to the 4th minus 2 cubed plus 2 squared minus 3 times 2 minus 6 all over minus 8 times 2 to the 5th. Oh, sorry. I skipped ahead a term. My bad. Let me actually write all of the terms. I know, crazy. So 2 to the 5th minus 8 times 2 to the 4th. There we go. Let's see, plus 13, 2 cubed, minus 5, 2 squared, minus 12 times 2, plus 36. Okay. So all I've done is plug 2 in for x everywhere. Now I'm going to compute. All right, let the madness begin, right? So 2 to the 4th, so that's 4 squared is 16, minus 8, plus 4, minus 6, over 2 to the 5th, 16 times 2, so that's 32, minus 8 times 16, oh boy, so that's 128, I guess. 13 times 2 to the 3rd, so that's 8 times 13, so that's plus 104. Minus 5 times 4, so that's minus 20. Minus 2 times 12 is 24, plus 36. Equals. All right, so on the top we have 16 and 4 for positives, so that's 20, minus 8, minus 6, minus 6, that's minus 12, minus 20, so I'm going to get 0 on the top. Realize I'm computing this a little quick. You can feel free to pause the video and compute it if you want, but it's just straight up computation, so that's why I'm doing it sort of quick here. So positives, let's see, 104 and 36 is 140 plus 32, so that's 172 versus 128 and 44, so that's 172, so it gets 0. Which we sort of expected because, you know, we mentioned we're going to use L'Hopital's rule, so that's maybe not surprising, but this is sort of good news. This is 0 over 0. So there's 2 ways of tackling this, right? Now we could try to do this straight up algebraically by factoring these things and trying to look for the common factor to cancel out. And that should work because these are polynomials and that is a thing that we can do. But they're also terrible polynomials, right? I mean, they're big, they're not really obviously factorable in any nice way. I probably have to do rational root theorem with synthetic division and stuff, and that's a mess, right? I mean, like, in fairness, since I know, right, that this is happening at x equals 2, and that's a 0, like, I sort of immediately know what the 0 is I want to pull out, so it wouldn't be awful. Like, I could skip the rational root theorem part and just do the synthetic division part. But, I mean, come on, right? Like, that's still a lot of work. So instead, I'm going to do L'Hopital's rule. So in particular, if I call this thing, so if I call this, like, actual function f of x, right, I'm going to say that the limit as x approaches 2 of f of x equals, now you don't have to write it this way, but this is sort of a nice thing to do. I'm going to write equals with a L apostrophe H above it, so that sort of it declares, right? I'm saying these limits are equal, by L'Hopital's rule because I'm going to write something that sort of isn't obviously equal by just sort of algebra, right? Because I'm taking a derivative in a sort of weird way. But nonetheless, I'm going to get the limit as x goes to 2 of, so now I take the derivative of the top and bottom separately, right? So I'm going to get, let's see, polynomial rules everywhere, so I'm going to get 4x cubed minus 3x squared plus 2x minus 3 over, and I'm going to get 5x to the 4th minus, let's see, that's 4 times 8, so 32x cubed plus, and let's see, that's 3 times 13, so 39x squared, and minus 10x and minus 12. Okay. So that's doing my polynomial rule term by term, right? Drop the power in front, subtract 1 from the power, go all the way through. Now again, I'm going to take this thing, and again off to the side to check, I'm going to plug in 2. So note, again, I'm not saying it's equal, because it may not sort of resolve nicely, so I got to write it off to the side. So I'm going to sort of write it over here. So I'm going to have 4 times 2 cubed minus 3 times 2 squared plus 2 times 2 minus 3 over. And this is sort of promising if we think about it real quick. I realize this is maybe not something you would think of, but all of these first terms are even, right? Even, 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 so their sum or difference will still be even minus an odd. Haha, I won't get 0. Probably. If I got 0, that would be strange, but I have high hopes here. Nonetheless, continue on. 5 times 2 to the 4th minus 32 times 2 cubed plus 39 times 2 squared minus 10 times 2 minus 12. Kind of evil person came up with this question. It's terrible. All right, so what do we got? So 2 cubed is 8 times 4 is 32. Minus 3 times 4, so that's minus 12. Plus 4 minus 3 over. Ew. Let's see this. So that's 16 times 5, so that's 80. Minus 32 times 2 cubed. So that's 8 times 32 is 256. Nice binary number. Plus 39 times 4, which is 160 minus 4 is 156. Minus 20 minus 12. So in particular, putting this stuff together now, I have 32 and 4 for positives. So that's 36 minus 15. So that's 21, not 0. Good news. And at the bottom, I have 80 and 156. That's going to be 240 minus 4, so 236 minus 256 is negative 20, negative 40, negative 52, if I did that right. And I'm about 70% sure I did that number crunching right, but you might want to double check just to be sure. I'm out here doing this on my feet here. So 21 over negative 52, but that tells me then, right, this limit is nicely resolved, right? It doesn't have a domain issue at 2. So in fact, this limit really does equal negative 21 over 52. All right. So that, as sort of annoying as that number crunching was, far superior, right, to doing synthetic division or any kind of like factoring craziness for this thing, right? So I could bypass all of that and just be like, haha, you know, L'Hopital's rule, I got my answer. Okay, so that's that. Hello. So in this example, we are going to compute another limit using L'Hopital's rule. But sort of oddly, this is not in a format that looks like L'Hopital's rule, right? Because L'Hopital's rule sort of requires that we're looking at something like 0 over 0 or infinity over infinity. This thing Definitely not that, right? In fact, this thing sort of looks like it's going to, right, if I think about what the infinity is doing, this thing is going to something of the form 1 to the infinity, which is still, right, an indeterminate form, right? Because you have that tension between something trying to stay small with the 1 as the base, but the infinity power is trying to like blow it up to, you know, a large thing. So how do we get it to be in L'Hopital's form? Well, a way we can think about this is we say, okay, let's assume for a moment that the limit exists, and let's give it a name. So in particular, I'm going to say, okay, I'm going to claim that the limit as x goes to infinity of 1 plus 1 over x to the x equals some L, some number, okay? And for those of you that sort of, you may have seen this before, this is actually a classic limit, but even if you have, you know, forget that part for a second, we're going to show how we get there, how we sort of get this limit. And if you have no idea what I'm talking about, don't worry about it. We're about to see what I'm talking about. All right, so let's say I call this thing some L. Well, what I could do is rewrite this thing. So in particular, I can think of this as L is the limit as x goes to infinity of e to the natural log of this thing. Now, I can do this. I actually don't need that it exists or equals L, because the e and the natural log sort of undo each other. But sort of some people like to do this by doing sort of natural log on both sides, and technically there's a little bit of an issue because you are assuming the limit exists and you'd have to show that first, but that's sort of a little beyond the scope of what we're doing here. I'm going to sort of stick to this form, but maybe I can show how it's similar if we sort of use it the other way. Regardless, using log rules, right, I have log of something to a power, so I can bring the power down. So I have that this is e to the x times natural log of 1 plus 1 over x. And in particular, this is actually through the fact that an exponential is continuous, but again, we don't really need to keep track of that part. I can rewrite this as e to the limit as x goes to infinity of x natural log of 1 plus 1 over x. So now my goal is to figure this thing out. And I could just keep writing it with like the weird, you know, equals e to the limit of blah, blah, blah the whole way down. But instead, I'm going to sort of compute this thing off to the side and then come back. So sort of, I'm going to pause here. So pause and do just the limit as x goes to infinity of x natural log of 1 plus 1 over x. Now, as x goes to infinity, x goes to infinity, shocking. But now natural log, right, the 1 plus 1 over x, the 1 over x is going to 0. So this is going to natural log of 1, which itself is 0, right? So this is looking like some sort of infinity times 0, which again is still an indeterminate form and still not the thing that L'Hopital's rule can sort of deal with. So what I'm going to do is rewrite it one more time by instead moving the x below. So I'm going to write this natural log of 1 plus 1 over x over 1 over x. Right? So basically what I did was I sort of thought of this as x over 1 and then divided the top and bottom by x. So in the top I get 1 and in the bottom I get 1 over x. Okay? But now, if I think about what this is doing, I'll do this in a different color. This thing is going to something of the form, well, that's 0 over, and then 1 over x, as x goes to infinity, is also 0. So now I finally have it in L'Hopital's form, right, after all this manipulation. So that means I can say this is equal by L'Hopital. Again, you don't technically have to write that, but it is a good idea, so sort of in terms of mathematician speak, people can keep track, but also in terms of like as a student, right? If your stuff is getting graded and you want to cite L'Hopital's rule, it makes clear that you are doing the right thing instead of some crazy thing, okay? So this is equal by L'Hopital. to the limit as x goes to infinity. So now I'm going to take the derivative of this thing, which is the derivative, right, of a natural log. So that's going to be 1 over the inside, 1 plus 1 over x, times, and then the chain rule, right? So then I have to multiply by the derivative of this thing. So that's going to be times, derivative of 1 is 0, and derivative of x, 1 over x, which is x to the minus 1, is going to be negative 1 times x to the minus 2. Right, so that's dropping the minus 1 in front, subtracting 1 from the exponent, which gets me that, all over. And then this, right, is x to the minus 1, so that's going to be minus 1 times x to the minus 2. So in particular, just cleaning this up a little, x, limit as x goes to infinity, so I'm going to have 1 over 1 plus 1 over x times negative x to the minus 2 over negative x to the minus 2, which is nice because this and this cancel, right? So this really is just the limit as x goes to infinity of 1 over 1 plus 1 over x. All right. So all of this craziness to get here, but now when I see what happens as x gets infinitely large, this term goes to 0, this whole thing becomes 1 over 1, so this becomes 1. Now here's where most people sort of get right to the finish line and then slip on the banana peel, right? So we want to make sure that we remember this is not the end, right? This was admittedly most of the work, but I'm not done yet. I've gotten all the way down to here, but this is this limit, right? So in particular, after having paused and calculating that limit, I'm then going to take this limit and bring it back and plug in to here, because that tells me that this equals e to what that limit was, which was 1. Or in particular, it is just e. So our original limit was 1 plus 1 over x all to the x, right? And I sort of manipulated that by doing e to the natural log, so I could use log rules so that I could look at, right, pulling the limit up here. And then I paused, I took this all by itself, and then I had to sort of move the x down in order to get it to a 0 over 0 form for L'Hopital's rule. So all of that got me to 0 over 0, so I can finally apply L'Hopital's rule. So I did that, took the derivative of the top and the bottom separately, and then it turns out that the chain rule canceled the bottom nicely, and I ended up with just this 1 over 1 plus 1 over x, which as x gets infinitely large, gives me 1. I took that and I replaced my limit, right? So I replaced all of this with 1, so it's the answer. This whole limit up here was really just e to the 1 or e, okay? All right. So this is the sort of classic definition. One of the ways we can define e is this limit, okay? So that is that.